out a revised schedule. It's got some highlighted stuff here. So those are places where I had to make some changes. So basically, I moved project check-in day to October 24th. Friday, October 24th. So it used to be, yeah, it used to be class 19, October 20th, Monday the 20th. So I moved it from Monday to Friday. And then I just moved up the things that we were going to cover. So I'm going to cover them Monday and Wednesday, and then Friday will be project check-in day. Reason for that is that I am not going to be here on Friday the 24th. So that's going to be project check-in day just for you guys to discuss. And Ian said he was going to try to pop in and answer questions as well. So your project check-in day has moved. And I also moved the due date because Steel Drum was supposed to be due the following Monday, right after project check-in day. So I moved it so both Steel Drum and Pipeline are due on the 29th. So both projects due on the same date now instead of the staggered. Okay, so today we're going to discover formulas for the derivatives of exponential functions, and we're going to use them with other derivative rules like the product rule and the quotient rule and the chain rule to solve optimization problems. And we've actually been doing this a little bit informally already. Today we're just going to officially learn how to take the derivative of an exponential. Okay, so can you apply the power rule to e to the x to take the derivative of e to the x? No, the power rule only works when x is the base, number is the exponent. X to the 5th, x to the 7th, right? X has to be the base, number has to be the exponent. This is reversed. We have a number as the base and the variable as the exponent. So this is a big old no. So in the group activities last class, we conjectured a formula for the derivative of e to the x based on its graph. So here's the graph of e to the x. If I was going to try to sketch its derivative, sketch the derivative of this function, is there a place where the derivative is 0 or gets really close to 0? Negative infinity, right? As we head out towards negative infinity, if I have little tangent lines here, they're getting flatter and flatter and flatter and flatter as you go towards negative infinity. So the derivative is approaching 0. And then what does the derivative do as x approaches positive infinity? It gets larger and larger and larger. So the graph of the derivative of e to the x looks just like e to the x, right? As the x goes to negative infinity, the tangent lines get flat, so the derivative is approaching 0. And as x approaches positive infinity, the tangent lines are getting really steep, so the derivative is going up quickly. All right, so I'm going to skip number 3 there. So the book proves this surprising fact using a method other than just drawing the graph. It's worth a read, but we're not going to do it in class. So it turns out that the derivative of e to the x is e to the x. Easiest derivative rule ever. Derivative of the function is the function. It's not too hard to differentiate an exponential function that has a base other than e. If you want to take the derivative of a to the x, it's just a to the x times the ln of a, times the ln of the base. Okay, so that's for any base, including e. You can use this same rule for e because if you take d dx of e to the x and you follow this rule, it says that would be e to the x times the ln of e, but the ln of e is 1. Right, so this is e to the x times 1, which is e to the x. So a to the x times the ln of a is the more general rule. The derivative of e to the x is e to the x is a specific case when the base is e. It's a product, so there's nothing you can do to combine them. You mean a to the x times the ln of a? Yeah, there's nothing you can do. Look, times the ln of 3. Ln of 3 is just some number, so it's like, oh, you can't, oh, I get what you're saying. Okay. Yeah. So Yeah, 3 to the x times the ln of 3. Even if it was 3 to the x times a simple number like 5, right, that is not 15 to the x. You can't, because the order of operations says you'd have to do the exponent before you can multiply. So in general, there's no way to simplify those two things. Okay, so let's use our new rule to take the derivative of 4e to the x plus 6 to the x plus x to the 6th. All right, so what's the derivative of 4e to the x? 4e to the x, right? Easiest derivative rule there is. Okay, plus, what's the derivative of 6 to the x? Close. 6 to the x times the ln of 6. Plus, what's the derivative of x to the 6th? 6x to the 5th. That's it. What do you mean by solve it? Get a decimal approximation? Generally, no. Yeah, so mathematicians generally like to leave this. This is exact, right? If you put it in your calculator, you're going to get a decimal approximation, which is not exactly equal to the ln of 6. Because ln of most numbers, except for like e and 1, are irrational. They're those decimals that go on forever and never repeat. Why? Because of the chain rule? The ln of 6 is a constant, right? So if I was going to take the second derivative of this, not a bad idea. Let's do right, so the second derivative, 4e to the x, would be 4e to the x again, plus. The ln of 6 is just a constant, so it's just going to come along, right? Ln of 6 times, and then the derivative of 6 to the x is 6 to the x times the ln of 6. And then the derivative of 6x to the 5th is 30x to the 4th. And here you could simplify. You could write ln 6 times ln 6 as ln of 6 squared. It is, but the derivative of a constant times something, when you have a coefficient, like say d dx of 6x, right, is 6. Right, so the derivative of 6 itself is 0, but we were taking the derivative of the ln of 6 times 6 to the x. So now it's a coefficient. So it just comes along for the ride. You just copy it down, then take the derivative of the function. Okay, one last thing I want to add right here where we had d dx of e to the x equals e to the x. What is d dx of e to some stuff? What does that equal? E to some stuff, yep. Times the derivative of the stuff. And you could write times the natural log of e, but we don't need to because the natural log of e is just 1. And how about if I want to take d dx of a to some stuff? What would that be? Times the derivative of the stuff. You got it. That's times. Okay. All right, so that's it for me. You guys can start your group activities.